So let's have a break for 5 minutes. So just out of interest, did anyone think about this thing? Like, that hasn't seen this picture before? Like, what would you... So I have this growth and deep group, I have all these operators. What might be an interesting question to ask? Very open-ended question. But does anybody have a...
I would wonder what is the alpha generated by these smaller things.
These operators.
Yeah.
So we have this, you know, we have sim. And then we have these operators, kind of E alpha, EA, and FA. And they're operating on it. And, you know, what's this algebra? Very interesting question. So, you know, when we did this just for H1 and H1s, sorry, HM and HM star, we got the Heisenberg algebra. Yeah. So what's this algebra? So now, let's do some lead theory for a second. So, if you have a simply laced thinking diagram, you can associate a Cartan matrix, M alpha beta, where M alpha beta is 2 if alpha equals beta, minus 1 if alpha and beta are connected, and 0 otherwise. That's how you read the Cartan matrix of a simply laced thinking diagram.
And this is can go both ways, right? For a suitable Cartan matrix. Yeah.
Yeah. And then you can associate G, which is a complex semi-simple Lie algebra, as the Lie algebra generated by P alpha, F alpha, and H alpha, subject to beautiful relations. So the relations are that P alpha, F beta is delta alpha beta H alpha. So if E alpha and so what you like, if you're in Lie theory, you should have the relations of SL2 imprinted in your brain, which means that I better not screw them up. Okay, so these are the, if I leave away that E alpha, F alpha is H alpha, these are the 3 relations in SL2. And now somehow this Cartan matrix tells me how to glue together a whole lot of copies of SL2 to make a beautiful complex semi-simple Lie algebra. And so here I should write H alpha and beta is M alpha beta. It's minus M alpha beta. Yeah. And then there's one more relation, Serre relation. So yes, Serre relation. I don't quite remember it at the moment. That's obviously not implanted in my skull, but I'll tell you why in a second. So here we have V. So this is a complex semi-simple Lie algebra.
Like a finite type.
Yeah, that's what I mean by simulating the background. You know, totally amazing. You know, like E8, very complicated Lie algebra, but somehow you can give an incredibly efficient, simple presentation for it. Totally mind blowing. If V is a finite dimensional V module, we say the Cartan is the direct sum of H alpha, and then V breaks up into weight spaces, V lambda, lambda is H star, where V lambda is the set of all V in V such that H alpha dot H dot V is lambda H V all H in H. The weight space, and then E alpha maps from V lambda plus alpha, etc. And one thing that's kind of, I think, remarkable is that if I have a module which satisfies the, and I have operators E alpha, H alpha, and F alpha that satisfy these relations, and it's finite dimensional, their relation is automatic. Okay, so in many cases you don't actually need to remember the their relation.
Wait, as in, can you just repeat that statement?
So I have a finite dimensional vector space. It has a decomposition into weight spaces. And I have operators E alpha and F alpha that satisfy this. They satisfy the SL2 relations. Then their relations automatic.
It's only an infinite dimensional whack.
Yeah.
Wait, you need the interaction relation H alpha E beta. It's not just SN2, right? You really need those three relations now?
I need E, yeah, you're right, exactly. I need also E alpha commutes with F beta
Yeah.
when alpha and beta are not equal.
You read that.
Yeah, sorry. I need these.
Right. It's not quite SN2, it's a bit more.
Yeah, that's true. Good point. Absolutely, is that still true? I think so, in interval, yeah. Not sure, but think so.
I think that's right.
So now we get some back to sim. So we set HA with the commutator of EA and FA. So by sim, I mean we have sim and we have these operators EA and FA, which is defined with the class of EA, class of FA. Or you could just say, I have this vector space spanned by partitions, and I have these operators given by this rule that I wrote over there before I erased. Yeah, so we're adding and removing boxes if we're that. Now, play it. There's two easy things and one thing that's very good. The first thing is that HA dot lambda. So this is a basis set element corresponding to a partition. So this is E alpha. So what is this operator? This is E A F A minus F A E A. So what this does is it FA removes an A box, EA puts it back. Here, EA adds an A box, FA removes it. So this is a weight vector, and the eigenvalue is the number of removable A boxes minus the number of addable A boxes times lambda. Okay, so our partitions are indeed weight vectors. 3. Whoops, 2. Is that this the relation that Daniel was worried about? EAFA prime is HA if A equals A prime and 0 otherwise. And this is saying that the operators of adding a box or removing a box commute if they're distant. So if I have like a box of content 7 and a box of content 5, this is saying removing or adding an A box is the same. And then in the case where A and A prime are one away from each other, this is something very easy that like T alpha, EA, is 0 or something. But anyway, it's like I claim this one I already proved, and this is easy. If you think about it for 2 seconds. And then the one that's like
the first one removed is these numbers, so they just
1 or minus 1 or 0?
Yeah, exactly.
Yeah.
These are in
Yeah.
0, 1. And when we go on P, they won't be in 0, 1. And this is a little bit subtle. So if we write alpha A to be it's very subtle, and I mean it's a little bit subtle and also very fun. HA plus HA plus 1 HA minus 1. Okay. Sorry, I mean something slightly different here. So we have H, which is the direct sum of these HAs. And then we consider H dual, which is the direct sum of lambda i's, so this is A and Z. And
Not to be confused with the HAs that we already defined, I guess, right?
yeah, it's true.
Just,
Yeah, sorry.
it's fine.
So this is the dual basis.
You want to see this somewhere?
Sorry.
You want to see the next space?
And then I consider these things, which, if you look at it, this is exactly the rows of an infinite Cartan matrix. So on the diagonal, or yeah, almost the rows, minus the rows of an infinite diagonal matrix. So on the rows I have -1, 2, -1. So the claim is that basically, if V is in the new, then E alpha of B is in V plus alpha A, and F alpha dot B is in U minus. So what it's saying, this is giving you a precise recipe for how these values of addable and removable boxes change when you add an A box. It's saying it doesn't affect anything except for the number of addable A minus 1 and A plus 1 boxes. So it doesn't affect the number of addable or removable A minus 1, A or A boxes. Sorry, say wrong about that. So we're applying this operator of adding an
An A box.
we're applying this operator of adding an A box. And we're asking, how does this count, this quantity, change when I do that? And the claim is that it doesn't affect this count for A prime, where A prime is not A minus 1, A or A plus 1. It's very believable, yeah? So that's saying that adding a box on an A diagonal only affects counts around that diagonal. So that's easy to see. The little tricky thing, so this is a little combinatorial exercise, is to see that it affects the other counts in a very precise way that's only depends on the content of the box we're taking. And when you do this exercise, so this is an exercise. I don't know any way just to see it in an instant. I break it up into cases and then every case works miraculously. Kind of quite subtle. I think it's a little miracle.
Maybe I'm just confused, but I would have expected it to be like negative what you wrote down. But I would expect like alpha A of HA to be like 2.
Yeah, I might have screwed up EA and FA.
Oh, maybe. Okay, that's the reason why. That's fine.
I'm a little bit confused. Yeah, I'm a little bit confused about your remark. So the claim is that we start with something sitting in VNU.
Yeah.
By EA to it naturally, we want to know where it lives.
Yes.
Uh-huh.
Sorry, this is now a weight vector, not a pattern.
Weight vector. Uh-huh.
So this is a count saying that I have so and so many addable blah boxes. I can think of it as an infinite row of numbers. And then I'm applying EA and it's saying these numbers change in a very precise way. Yep. So let's just do this one. Like, what's this? The count here. So this has no addable I boxes for I not equal to 0. And then it's it has one addable 0 box and no removable 0 boxes. So its weight vector is minus lambda 0. This is red. It's minus lambda 0. Now, when we add it, what's the count here? This has an addable 1 box, an addable minus 1 box, and minus lambda 1 minus lambda minus 1, and it's got a removable lambda 0 box. And you'll notice that this is exactly this plus the quantity that I wrote down there. So, I don't know, like maybe if you're an expert on this stuff, it's like totally clear that that's the case. But for me, when I look at it every time, it seems like a little miracle. So now, the conclusion of this. So before I said I start with a finite Beacon diagram, but I can also start with an infinite Beacon diagram. Minus 1, 0, 1, 2. Minus 2. And then I can apply the same process and I get SL infinity. So it has generators EI, FI, and HI, or I in the integers. And then I claim that those three things that we checked over there, the claim implies that theorem is that EA, FA generate an action of SL infinity on C. So I think that one is used to the fact that like, in Lie theory, often like quite rich combinatorics shows up. But I feel like this is probably the most crazily beautiful example of it. Yep. So we have space of all partitions. This is naturally a module over SL infinity. Totally crazy good. Yep. And just a remark is that sim is isomorphic to L of lambda 0. So it was basic.
So if I want to think of these as infinite matrices, can I do that?
Yeah.
But where do the matrices start? Because like
Yeah, so it's Z by Z matrices, in which every row and column has finitely many entries and then trace 0. So
Or I thought it would just be that it's a finite support matrix, right?
finite support matrix. Yeah,
finite support matrix. Yeah, exactly.
great.
And probably I need then I'm allowed to say trace 0 and 100.
That's right.
And
So sim, can you just remind me, the sim is the category here or?
so sim is this. It's a space of symmetric functions, but you can think about it as a direct sum. Probably I'm thinking it secretly over C, where partitions make. So it's just a vector space with basis all partitions.
Sorry. Alpha A should, I guess it seems like it should be negative what you're at, because here maybe I'm confused, but you're adding it, and so right?
Yeah, I think if I switch my FAs and EAs, you're happy.
No, isn't the operator, maybe I'm confused, empty set the first box, it's E0?
This is E0, yeah.
Yeah, and so alpha A should be negative what you're at.
I think Alex is right, there's a slight
Oh.
mistake.
Yes, perfect. And then that mixes up the. Thank you, that's great, yeah. Great, and now I think everything's okay.
Okay.
Thanks a lot. So. Maybe it's just like, I don't know, just to appreciate like how. I just find this like totally amazing and beautiful. And just to appreciate it a little bit, let's think about good old SLN. Okay, so SLN, the algebra of n by n traceless vectors. So if you know highest weight theory, you know that this has a whole lot of highest weight modules, and their character formula is given by Weyl character formula, and it's not that easy. But SLN has the fundamental representations, which are given by the exterior powers. So SLN acts on Cn. And then we have the fundamental representations, which is SLN acting on the nth wedge power of Cn. Okay. And so this would be the simple module of highest weight lambda 1, and this would be the simple module of highest weight lambda. So if you are a Lie theorist, you're used to like finite dimensional Lie algebras, you've got this kind of world of like complicated representations out there, but the fundamental representations like these are generally pretty easy. You know, these are kind of our bread and butter. Now, what this is saying is that the bread and butter for SL infinity is already this crazy space of all partitions. This is like one of the easiest representations to write down, this basic representation. You should think about it as some kind of analog of this natural representation. And already there's this incredibly rich common point. Okay.
But we do have a simpler representation just by the matrices acting on like the generators. Right?
Yes.
Like, and is this like some functor applied to that thing? Or
Yeah, so the really important thing for, yeah, so I won't get to the end, but it's also good to chat. So yeah, so there's Cn, like SL infinity acts on C infinity. One issue is that this is not highest weight.
Depending on if you're using Z, then yeah, I guess it's confusing since now. Like,
and the more important thing I think is that when you like I think I've done this thought experiment with you before, with some of you before. That imagine that all you care about is SO3, and you're like happy SO3 has one representation in every odd dimension, and you tensor them together. It's a bit complicated, but you're cool with it. And then someone comes along to you and says, actually, Geordie, there's SU2, and it's the universal cover of SO3. And then your mind is blown because everything gets so much simpler, and then you love SU2 until the end of your days. So something similar happens with affine Lie algebras. So people start off studying loop algebras like SLN CT. So this would be an example of a loop algebra. And these are important, show up in lots of kind of mathematical physics, etc. But then someone comes along and tells you, this thing actually has a central extension. And understanding representation of that central extension somehow like unified the theory enormously. And so then you become convinced that you shouldn't study the representation theory of that, but you should study the representation theory of the central extension. Now this is a level 0 representation, which means the center acts trivially. Whereas this is level 1. And somehow once you have level 1, then you can generate all the higher levels. So that's another reason why it's extremely important. So you really see the need of the central extension when you look at this basic representation. Okay. So would you like more raves? This is Hecker algebras of roots of unity and crystal bases of quantum affine algebras, Lascaux, Leclerc, and Thibon. Very famous paper, LLT.
That's cool.
Lascaux.
That's cool, Leclerc, Thibon.
Yeah. Then what did I say?
You missed Lascaux.
No.
No? Okay.
Okay, so here's the paper, 97, I think, 96. So I think it's very interesting to read the introduction of this paper as an illustration of kind of how mathematics works and where great ideas come from. The introduction, this article arose as an attempt to understand the extensive numerical tables published by James in the appendix of 14. These tables contain some decomposition matrices of Q-sure algebras at roots of unity, which contain the submatrices of decomposition matrices of Hecker algebras. So James has this wonderful paper where it's called something like the decomposition numbers of GLN and related things for n up to 10. Can't remember. Anyways. So, and in the appendix of this paper, he just has a whole lot of tables, which are really extensive computations of decomposition numbers. So the subject of this course earlier. Okay. And then the second paragraph, a major problem in p-modular representation theory, blah, blah, blah. Decomposition matrix can in principle be expressed in terms of certain inverse affine causality polynomials. So they're answering a question which in principle, some smarty pantsers around the world know how to answer already. But it involves some polynomials that no one can work out. It's very complicated. So they say, unfortunately, these polynomials do not seem to be easily computable. The aim of this paper is to present a fast conjectural algorithm for calculating the decomposition matrices of Hecker algebras of roots of unity. So that's all modular representation theory, yeah? And then they say, this algorithm is actually designed for solving quite different problem, namely to compute in an efficient way Cauchy-Warren's global basis of the quantum affine algebra, okay? So that's already kind of a wacky change of direction. You know, at this point in the mid-90s, I'm not sure, maybe Andrew can correct me, but I don't think many people studying modular representations of symmetric groups knew about crystal bases of affine algebras. Yeah. So, blah, 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 blah. And then I just find this introduction really remarkable because it's very clear that they're deeply and intimately aware of two very different problems and connect them. So there's this whole world of like affine algebras, crystal bases, etc. And then there's all of this, you know, very specialized work that people are doing in modular representation theory, and this paper connects them. And also I find it interesting because these Lascaux, Leclerc, and Thibon are all combinatorialists. So they, you know, they're very much looking at the world through a kind of ability to compute and parameter sets of things. And they just notice like this crystal basis is looking like something showing up in James's work, etc. So the moral of this is it's very important to be aware, try to be aware of what's going on in the mathematical universe.
So I think I've actually motivated many by Kleshev's work.
Yes, they say that too. Yeah, yeah. So Kleshev has these branching rules, but if you take a representation of a symmetric group, restrict it down to Sn, restrict it down to Sn minus 1. It's basically incredibly hard to understand how that decomposes. But what Kleshev pointed out is that understanding the socle is tractable. And then he wrote down these rules for understanding the socle in terms of p-regular partitions. And they started noticing this is exactly the same rule as the crystal graph of a quantum affine algebra. Just kind of mind-blowing observation. Yeah.
It's also a great example how important calculations actually are.
Yeah, exactly.
The tables.
Yeah, you have this appendix and people stare at it. And like, I don't know, I love reading James's papers because he's very much like, he's just like, I just want to see what's going on. I'm just going to work stuff out. And then, you know, he really presents things in the ways, like he says explicitly, I'm presenting this in a way that will try to make patterns as evident as possible. Okay, so that was the end of that. Okay, so also just one remark on this is that from one point of view, this is a very simple module, like not in a precise sense, but just notice that all the SL2 strings have length 1. So I have length 2. Okay, so if you know the representation theory of SL2, the simple modules look like this. You have raising operators, which are called E, and lowering operators, which are called F. And there's one simple module for every length. So the length 1 is the trivial representation, length 2 is the natural representation, length 3 is the adjoint representation, etc. And so you can look at a big representation of a Lie algebra, of a complicated thing, and restrict it to these SL2s inside and ask how does it break up? And these are called SL2 strings. And very important. And the point here is that in this basic representation of SL infinity, all the SL2 strings are length 2. Yeah. So if I can add a box of a certain content, I add it, and then I can't add any more of that content. That's what's taken.
Stupid question. I would say lengths 1. I would count the edges, not the vertices.
You know what I mean?
I certainly do, yes.
So now we go to characteristic P combinatorics. I just find it like, it's one of the wonders of representation theory that somehow something coming from this affine Lie algebra business, which comes from conformal field theory, is somehow related to mod P representations. This seems totally amazing to me. It's a connection that's really remarkable. So, characteristic P. So now we have SLP that. This is an affine Lie algebra, and it's associated to the P cycle, which is not a Lincoln diagram, but it's an affine diagram. So 0, 1, 2, 3, 4, 5, 6, 7. Okay, so this would be SL7. For the vertices, my direction is here. And this is generated by PI and FI. And now, exactly the same considerations as before tell us that sim as an SLP hat action given by P pi lambda is the sum over mu, where lambda goes to mu is a box of content I mod P. F alpha, Fi of lambda is the same sum of mu goes in lambda mod P. Okay, so we take all these things and let's just do modulo 2 in this picture. So these become 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. What was this one? This was 0, 1, 2, 3. So now we just have two operators, E0 and E1. 0, 0.
1, 0. The bottom one is 1.
Sorry?
The trivated vertex there can't have 3 zeros. The bottom one is a wait. No, you're right. Okay.
Okay. So now this is the action of SL2 hat on C. And, you know, it's not difficult, so that you can either check again using the same, essentially the same claim that I gave before, that this gives you an action of SLP hat, or you can be fancy and there's a kind of interesting embedding of SLP hat into a completion of SL infinity as some kind of periodic matrices. And then what we're doing is we're just restricting this representation under this embedding method. It's probably easier just to check directly.
Is that periodic embedding like the algebra side equivalent of trying to quotient out by the moving down by P?
Absolutely, yeah.
Getting an array?
So you want to take this string and roll it up. And that gives you this embedding thing.
What is sim now? It's not,
It's same vector space.
But now it's
but
more
it's not representation. It's still representation.
Still symmetric. I mean, sim is like sim without blackboard bold has always been symmetric polynomials. A vector space with bases given by partitions, by the short functions.
But the theorem you had before is not true. That it's the same as the Grothendieck ring.
No, it's not the Grothendieck ring of. It's the Grothendieck ring of characteristic zero representations. It's not the Grothendieck ring of characteristic P representations. Exactly.
Do we need to be characteristic P to have this embedding from SLP hat into SL infinity?
No, this is all. So the thing acting, like, this is over C.
Oh, right.
It's super important that, like, the thing acting Grothendieck groups are characteristic zero. Thing acting is. So this is an affine Lie algebra over C that's acting. And just as an example, it's as before with Alex's caveat. H is we can define this direct sum C H A, where A will be 0 to Z. And then we have H dual direct sum C. And then HA dot lambda is the number of removable boxes of content A mod P minus number of animal times that. And I just want to emphasize, like, this parallels what Chris just said. This number is in C. This is not a mod P number. And then recall another important remark here is if you just look at this module now, it already looks decently more complicated just as a representation of an affine Lie algebra. So one place where you can see this complexity is that the SL strings, SL2 strings now can be arbitrarily long. So if I start off here and I apply my zero operator, I go over here. Now I apply my zero operator, I split up. And now I apply my zero operator again, and I'll get to and then it stops. But by taking bigger, and if I take my one operator now, this will go don't survive quite a long time before it does. Then if I apply my zero operator, it'll let it survive for even longer. So the SL2 strings are arbitrarily long. And now, recall, given lambda a partition. So here's a. Partition. That a P ribbon is a connected sequence of P boxes which is removable. Okay, so here's a picture of a 1, 2, 3, 4, 5, 6, 7. This is a 7 ribbon. And a P core is a partition from which no P ribbon can be removed. And I think, I can't remember if we saw this before, but
We did that in the discussion last time.
oh, okay, yeah. And we know that blocks of symmetric groups are given by P cores, yeah?
These correspond to like strings along the imaginary direction in terms of the weights of the
Absolutely.
Okay.
Yes,
because it's the sum of all the fundamental elements, key things. So
exactly. Yeah, that'll be what I'll explain at the beginning next week. 2 weeks. Yeah. So lemma. Lambda mu same P core. So I didn't say what the P core, so of lambda. Maybe this is not correct language, but P core of lambda is keep removing P ribbons until you can. Any more? And what you're left with is the P core, and it doesn't depend on any removed. And lambda mu have same P core if and only if. So this is already just a hint that there's very lovely stuff going on. They lie in the same. H weight space. This is the carton inside it. Okay, so weight spaces are indexed by P cores. I think I wanted to give a little idea of this proof, but maybe. So proof is lovely, but I will skip it due to time. So connection to modular representations.
because it doesn't have the derivation, that's why. Okay, this makes sense.
Yeah, that's an important remark there. So what weight space is a little subtle in a affine algebra. And what Alex just said, I agree with. So here, CSN is the same thing as partitions. Here, FPSN is the same thing as P regular partitions. And this is the same thing as the thin index is the project, which is in decomposing the projective. So, and also we have the decomposition map from rep CSN. Rep FP SN, decomposition, that's a surjection. And we also can look at proj over FPSN. And by lifting, we can embed that inside rep, lifting and extending scalars. So this is the E. And somehow if we go form, then that's the C. So I'm just writing down this little C triangle. And also we have EA and FA, which act on sim. So now I'm FP. So this is the direct sum over all n bigger than or equal to 0 of the rep FPSN. And here there's a generalized eigenspace. H1 and H1 star. And note that as summands of some module, so like induction preserves projective modules. If I induct from Sn to Sn plus 1, that preserves projective modules. And then if I take a summand inside that, that's still projective. So these also preserve projective modules. And so, this is the last board, and then
Did you say what P regular meant?
I didn't. So that means no part repeated P or ordinals.
Yeah, we called that P restricted last time.
That's what we're doing.
Did I get the wrong name?
Which one is the correct one?
That's regular.
Regular? Okay, then I got it wrong.
Okay, so all the upshot of this is that we have proj over FP. The growth peak of this group of this sits inside sim FP, so sorry, sim C. And that surjects onto sim FP. And these, so this is the thing that this is just sim. And these are a little bit mysterious in at this stage. So we know as a vector space how big they are, they're given by P regular partitions. But I just want to remark that this can be described in terms of symmetric functions. So if you look, for example, this quotient is the quotient generated by power sums with exponents divisible by p. And then I just want to have this theorem on the board because when we come back to it, I'll begin with this theorem and then add some source next time. But it's very important to be able to digest this a little bit before we launch into it next time. So just as before, we had SL infinity acting on the direct sum, the Grothendieck group of the direct sum of all symmetric groups. Mod P, we have SLP hat acts on this. And this is again isomorphic to the basic representation. Basic representation. Zero. blocks. Blocks of FPSN correspond to weight spaces with so I'll explain what this means later, but Alex, yeah, anyway, that's related to Alex's question before. And blocks with same P weight two blocks have the same weight, P weight, if and only if the weight spaces. The weight space of the conjugate in the upper boundary. So let me just draw a picture, just so you have a picture in your mind before we return into next time. P weight, I also didn't define that this is the number of P ribbons removed to reach people. And you should think about it as basically how complicated your block is. So if this number is 0, that means you're already a P core, which means you're semi-simple. So the picture is the following. So
the right hand side there only has like n worth of stuff. You don't have many orders.
exactly, yeah, which is surprising. Okay, so let me just draw a picture that's trying to explain what's going on. So let's pretend that SLP hat is SL3. And then I take a finite dimensional rotation. And then I draw the weight spaces like.
Wow, that is amazing.
Yeah, there's my 0.
Quite hard to see.
But it's so symmetric.
But it's
how did you do that?
it's very
Very impressive, yeah.
Oh God.
Okay, so these are all the weight spaces. So this is my module, and these are all the weight spaces, yeah? With this is my highest weight module of highest weight. This is my highest weight. Now, what do I know from Lie theory? Basically speaking, so these extremal weight spaces. So I have this affine Weyl group action. Sorry, well, affine Weyl group is S3. Okay, so
where affine is in.
I'm pretending that SLP hat, which is this incredibly complicated thing with this infinite dimensional representation, is in fact SL3, and I have a finite dimensional representation I can just draw them. I'm also pretending that affine Weyl group, which is a very complicated infinite group, is in fact S3. Not true, but anyway. Now, and this is the action. So one thing that we do in basic Lie theory is we say, oh, the Weyl group acts, and it'll give us an isomorphism between weight spaces if they're conjugate under the Weyl group. And so this would be C, and then I immediately conclude that all of them is C. Yeah. And then in Lie theory, we learn that as you go in, stuff gets harder. And so like, this is much harder. you know, this is, like, if I could draw a much bigger picture, then this would get bigger and bigger dimensional, and it's much more complicated to understand what's going on in the middle here. Yeah, but we still know that we have an affine Weyl group. Okay. And then probably this would be. Okay. Now, the mind-blowing picture that emerges is that this whole picture is categorified. So each one of these dots corresponds to some block of some symmetric group. So here I have all of the blocks of my symmetric group laid out as the weight spaces in this picture. Okay. And also, this p weight is basically like how far I am towards the middle. So as the p weight increases, my categories become more and more complicated. And then what trinomial PA do is they upgrade the Weyl group action to a derived equivalence between these. So these are all very complicated categories, but they're all derived equivalent. And somehow so this says that if you look at all blocks of symmetric groups, you know, it's incredibly complicated spectrum of representation theory. But if you look at them up to derived equivalence, they're just given by a single integer, namely the p weight. And then there's a final step, which, in order to get Brouwer's conjecture, which is that within any affine Weyl group orbit, there's a particularly easy block, which one can then establish Brouwer's conjecture for. And so, yes, I just want to emphasize this picture that you get this incredibly rich family of derived auto equivalences from this categorification picture.